make sure you contact your advisor. There's nothing more annoying than when I have to track you guys down. So if you're with me, you would have already gotten an email from me. You should have already gotten emails from your advisors, I would imagine, right? Does anybody have any last minute questions on homework before we sort of move on?
I have no clue what homework 5 is.
Well, we covered it. Didn't we do most of the problems in last week? I think we did. Let's just double check before we go any further. Man, I am thirsty. I found a cute book that I will recommend to you guys. I think if you're serious about learning proofs, it's $10. I think you should think about getting it. I just ordered it. I'll show you. I saw that someone recommended it. I said, this is a great textbook for you guys. Well, it's not a textbook. It's a great. Yeah, I think we did. We did everything homework 5 last week. So check your notes, Mackenzie. The only one it's, don't forget, let me be clear because I know we spent some time on it and I think what I'll do is I'll assign it as extra credit. So, number 7, excuse me, number 8. Number 8 on homework 5 is tricky and I'll assign as sort of extra credits for anybody who wants to try it. We spent some time on it. I would encourage you to think about it. It's not an easy problem. In fact, it's quite tricky, but it is one that if you get clever enough, you can make sense of it. Anyhow, very good. Yeah, when is the quiz due? That's another thing. So I did post a quiz. If you have any issues, it's not hard. I think it's like 7 or 8 questions. Most of them are pretty straightforward. Please do the quiz, get your points. That would be my sort of advice to you. Yeah.
What are office hours like on Thursday?
My office hours are Thursdays. I don't know. I'm in class during the day, pretty much 8:30 to 10 on Tuesdays and Thursdays. I mean, look, I'm willing to meet. What does it say on the syllabus? I think it says I don't remember. It says by appointment, and that's really that. To be honest, that's the best way to go because they're asking us. No, I don't think it is, Michelle. I don't think it is, and Mackenzie says it's not. Well, no, but we'll trust you. So the question was my office hours. I mean, they've asked us not to or try to limit face-to-face, meetings. So the best way to have office hours is go in the Starfish and pick one of those times that are already pre-selected. And if those don't work for you, that's fine. Just email me. I mean, you and I have met a couple times already, right? So I'm happy. I'm happy to meet with you guys. And being that we have Zoom, they don't always have to fall in like traditional hours. If you need to meet at 7 o'clock or something at night, I mean, I can sometimes swing that stuff too. So the best thing for you is if you want to meet is to send me an email and tell me when you're available and we'll make something work. It's just, we're in some weird times. It's kind of hard to, make sense of all that stuff right now. All right. What we're going to talk about today is a very important, does that answer your question, by the way?
Oh, yeah.
Yeah. Okay. What we're going to talk about today is a very important sort of topic. And it has sort of, I don't want to say, well, I guess a good way to think about it is it shows up in pretty much every branch of math that we could teach you or you can learn. And so we think it's important and we're going to talk about it today. and it's called the cardinality of sets. So we sort of talked about this briefly when we talked about if we have a set, the cardinality of a set is how many elements are in it. So, I mean, look, one of the most basic things in this world that little children learn quickly and turns out to be useful in every aspect of life is counting. Counting. We count everything. Whether we're doing math for fun, we're doing math for practical purposes in the real world, counting is a fundamental thing. And so if we're going to talk about sets and we're going to talk about functions from one set to another, it's often useful for many reasons to talk about how many elements are in these sets. And so let's talk about that and let's remind you of a few things. So what we're going to do is we're going to discuss what we call cardinality. So recall, this is a, you know, what I'd like to say a fancy word for elements, or more specifically, the number of elements in a set. So for example, if I have some set A, let's say it's 1, 5, 10, 15, and 20. So that's it. We write A with vertical bars on each side, and we put that this is the number 5. Why? So let's write this as a sentence. If A equals this, then the number of elements in A is equal to 5. So very basic example. Let's do another one. Let's say this guy's B. And let's just, for fun, let's just say it's A, E, I, O, U, and Y. Aren't those the vowels, A, E, I, O, U, and sometimes Y in the English alphabet? I don't know. So if that's B, then the cardinality of B, or the number of elements in B, is 6, because there's 6 elements in there. And the question then becomes, you have these obvious things. So what about something like the natural numbers? Or what about, say, the cardinality of an interval? So think about this. It's a very clear idea. If we have a set that has a finite number of elements, it's very clear to us what its size is. We just count them. And so then we might be sort of, okay, we know the natural numbers are 1, 2, 3, 4, 5, forever and ever. We might say intuitively that that's some infinite set, right? That's kind of how we talk about it. But one of the interesting things is, if you look at the natural numbers or you look at the even numbers, the even numbers are a subset of the natural numbers. And they're both infinite sets in the sense that the pattern continues and you can't write them all down, although you can say something like this, which is let's call C the even numbers. And it's clear that C is a subset of the natural numbers. So what can we say about the cardinality of C and the cardinality of the natural numbers? And a more interesting question to kind of ponder that sometimes it might seem sort of very strange to think about it, but it turns out to be an important thing. You might ask, are there different quote unquote sizes of infinity? Now that seems strange to ask, but if you go to the previous page and you look at, say, the interval from 0 to 1, we think of that as every point on the number line between 0 and 1. And so for us, we at least our elementary and naive notion of sets, we would say, okay, this is an infinite set. And we would also say that the natural numbers are infinite, and the even numbers are infinite, and the odd numbers are infinite. But there's some little subtlety here where we might think, are there different sizes of infinity? Another way to think about it is think of a number line. How much space on the number line does, say, the even numbers take up versus how much space, quote unquote, on the number line the real numbers take up? And these are very cool things that are very difficult to actually answer specifically. But again, let me reiterate this. If I have natural numbers, 1, 2, 3, 4, 5, 6, and I said, I'm going to think about the natural numbers on this number line. How much space do they take up? Now you might say, what is he talking about? Okay, then contrast and compare that question with how much space does, say, the interval 1 to 10 take up if I include everything between 1 and 10. So these are questions that I want you to think about. They're not easy to write down. I mean, the question's easy to write down, but they're not easy to write down answers. So anyhow, ponder that, and we'll continue to ask you to ponder, but we're going to make a definition now. We say two arbitrary sets. So now I'm just talking two generic sets. I didn't tell you anything about them other than I have two sets. So we say the sets A and B have the same cardinality if and only if there is a one-to-one correspondence from A to B. Now, in this case, we write that the cardinality of A is equal to the cardinality of B. Yes.
When you say 1-to-1, you just mean like the overall number of elements, not the contents.
What do you mean? No, I mean a one-to-one function.
So like A is 1, 2, 3, dude, and 1, 2, 3.
No, but so you're hitting it. So the question was, what do I mean by one-to-one? Well, what this is saying is this is a mathematical way of saying two sets have the same cardinality if you can find a listing that associates each one in one set with another set. So, for example, if you go back to, say, C, and you compare C with N, there is a correspondence between each term in C and each term in N. Now, if that correspondence, if we can illustrate one that is one-to-one, then that means these sets have the same size. And for certain sets like C and N, there's going to be an I don't want to say obvious, but there's going to be a natural sort of function that you can see which maps C one-to-one with N, or vice versa. Does that make sense? So, for example, we're going to do that, and we're going to do that specifically in a minute. So maybe the way I don't know if I answered your question, but what we're going to define shortly is maybe is going to help answer the question better, because we're thinking now, if we go back to the question I asked on the previous page, what's the difference in, say, the difference between the set C and then the interval 0 to 1? And I think you're having a light in your head, Tom, because what you're noticing is one set you can kind of list its elements, you can quote unquote count them, whereas in other sets you can't. Can you list all the elements in 0, 1? Could you write down some sort of pattern? It doesn't seem obvious that you can. Turns out you can't, and we'll show you that soon enough. And that's a very important thing. But what we're saying here is that if I have two sets and I can find a one-to-one correspondence between the two, then, and what that means is I need a function that's one-to-one. Does that make sense? If I can find that, then I say they have the same cardinality. So we'll do an example right now. And we'll go from there. Does anybody else have a question before we do that? By the way, what is a one-to-one correspondence? That's a synonym for what? Starts with a B, ends with an action. Bijection. So one-to-one correspondence is a one-to-one and an onto function. Are we clear with that? I mean, I don't know if we are or not. These terms, it's really hard to understand how this stuff works if you don't understand the terms. So being a bijection or a one-to-one correspondence is a very, very, very sort of stringent set of properties that a function has, but they're very important. Anyhow, let's check out this example and we'll see exactly what I mean. Well, I shouldn't say we'll see. This stuff is not easy, of course. So let's consider this function, f of n equals 2n. And let's say, of course, that f is going from the natural numbers to the natural numbers. So let's just compute the first few values. What's f of 1? It's 2. What's f of 2? It's 4. What's f of 3? 6. What's f of 4? 8. This function f of n is a bijection. Now, even if you don't like these scary formulas, it's not hard to show this as a bijection, by the way. It meets the definition. So why is this a bijection? Well, let's see. Is it 1-to-1? Well, assume that f of n equals f of m. That implies that 2n is equal to 2m. And then if you divide by 2, that implies that n equals m. That's the definition of being 1-to-1. 1-to-1 means if two outputs are the same, their inputs must be the same. That is the definition. What about onto? Well, take some y in the natural numbers. Excuse me, not in the let me be a little more specific. I think I have a slight error here that I should clarify before we go anywhere. This should not be n here. I got to be more specific. Let me clarify this. I want to show that this function maps C. So what is C? Let's say it's 2, 4, 6, 8, 10. So I'm taking f. Think about this. Look where f goes. It takes any natural number and it assigns it to an even number. Okay, so what does that mean then? We'll take y in that set. So take y in the domain or the codomain, if you will. Then y over 2 is clearly a natural number. Take any even number and you can divide it by 2. Well, plug that into your function and you get 2 times y over 2, which of course equals just y. So that is the definition of being onto. So what we just did, let's take a step back because this is very conceptually difficult for babies. And you know how I say babies, I don't mean that, you can laugh, but you're amateurs, right? This is a big mind F. It's really hard to understand what we're doing here. We took two sets. I have I have the natural numbers. I'm going to take every natural number and I'm going to assign it to an even number. And it's a very simple rule. I take the natural number and multiply by 2. I mean, that's how you learn what the even numbers are when you're a child, right? You take the multiples of 2. My function f literally gives us the multiples of 2. Now, all I had to do was show that it was 1-to-1 and onto. Once it's 1-to-1 and onto, it is a 1-to-1 correspondence, or a bijection, if you will. And by definition, what this means is this means that C and N have the same cardinality. So another way of saying that is they are the same size. I mean, they're both infinite, right? But it's interesting because one's a subset of the other one. It's a very wild, sort of thing in your head. It's hard to wrap your head around this. Does anybody have a question? Stuff's wild, huh? I remember learning this the first time, and I was completely lost. It takes a lot of work and practice on your part to understand this. It just does. I know I sound like a jerk, I think, because I always say, hey guys, this is hard to learn. It takes a lot of time, but I'm not lying to you. It does. Like, no one just learns this stuff in 10 minutes. It takes some hard work. Okay. If, now this is going to be slightly different than what we just did, but if there is a one-to-one function from A to B, we write this. Or if you can show they're not the same, this. So this is pretty cool. What we're doing is we're assigning size to sets. Again, this is a very obvious thing if a set is finite. If there's only so many numbers in it, it's obvious. You count them. But for infinite sets, it's not. So the way that people figured out how to, quote unquote, give a numerical value to the size of something is using this. So here's an interesting thing, another definition. If a set A is finite or has the same cardinality as the natural numbers, we say A is countable. So here's the cool thing. There are certain types of infinities, we just saw it in the previous example, that we can list the elements, we can count them. Now the problem is we'll die before we finish, but we could, in theory, if we never died, count them. 1, 2, 3, 4, 5, 6, 7, 8, over and over and over. 2, 4, 6, 8, 10, 12, 14, 16. That set we say is countable because we can list its elements out. Now, we don't just want to say list out because that's kind of like not precise language. The precision, the precise language is if a set we can list its elements, that means that from a mathematical standpoint, there is a function f that is a bijection from that set to the natural numbers, or from the natural numbers to that set, if you will. Does anybody have a question about this? So here is the opposite of that. If A is not countable, watch how creative this word is. We say A is uncountable. Very creative language. So again, why would we want to use this kind of language? Well, it makes sense to us. Something like 2, 4, 6, 8, 10. We can list them out. There's a natural, obvious order there. So we say things that are like countable. That it turns out the integers are countable because we can literally find a pattern and list them out. If you wanted, you could go 0, 1, -1, 2, -2, 3, -3, 4, -4. You could even find a function that will do that. So before we do that, let's go back to our main example we've been bugging out on. So a good way to see these ideas is to visualize the sets. So for example, if I have the natural numbers, we know what this is. This is 1, 2, 3, 4, 5, 6, etc. And then let's put the set C that I've been using. This was 2, 4, 6, 8, 10, 12, etc. And the thing that you want to visualize that there is a sort of, there is a clear association between each term in one sequence with the C term or the equivalent term in the other sequence. You could visualize this function. Does anybody have a comment or a question about this? Yeah, you stretching? You have a question?
No, but that also did answer my last question.
Right. So you see that you got the idea. So I think what's happening here, Fink. I like saying that, Fink. If that bothers you, you can just say.
That's what everyone called me in high school.
Okay. What's interesting is we make a definition about two sets having the same cardinality, but the only reason we make that definition is for this sort of better idea, at least for us in this class, is that if you can take one sequence and list it in this sort of way you can see a clear association with your sequence in the natural numbers, this is a pretty special kind of property because we think of it as saying, oh, I can count that sequence. I can count that set, if you will. And by the way, you could think of these sets as a sequence if you wanted. And that's sort of what's really happening. What is this? What is by definition a sequence? It's a function whose domain is the natural numbers. And so if there is a natural connection between whatever set you have and a sequence, then we say it's countable. Now when I say natural, that's maybe poor language. It's not always obvious how you find the function that associates the two. So I can just draw this like I did here, and I say, okay, this one, this one, this one, this one. First, second, third. But we already exhibited the function too. It was f of n. And if you want to be explicit, what was our function? Our function was f of n equals 2n. Right, so look at this down here, the sixth term. When I plug 6 in here, I get 12, right? So you can think of it as just listing them in this nice fashion, or you can actually think of the function. Input, output, input, output, input, output. Does that make sense? Maybe, I don't know. I found as a student for myself, when I was a student years ago, I found these ideas very difficult to learn. They were very weird to me. Like, the first thing you say is, well, first off, we have this weird notion of what infinity is anyhow, or infinite size, right? Really, what does it mean to be infinite? Well, it means it's not finite. So finite means there's a beginning and an end, right, I guess. So it's very weird. Think about how we define these things. We said if you have a set, the number of elements is called its cardinality. So we kind of hovered around, what does it mean to be finite? And then we say, if your cardinality is a finite number, you are a finite set. And then from that, you can define an infinite set by saying any set that's not finite is infinite. Do you see how we're logically defining these things? And now we're going to do the same thing. Now we're saying, okay, cool. Now we want to look at these infinite sets that have this correspondence with the natural numbers. Any infinite set like C that I can line up with n, and I can see a correspondence. And it's not just the even numbers. I can do this, you know, with, say, the odd numbers. Let's say, oh, I should have used E for that set. But if I take the natural numbers, 1, 2, 3, 4, you know, we can go out here to say like 100. And then 101, if you will. And then let's take the odd numbers. I'll call it O. What's the first odd number? 3, 5, 7, 9. What's the 100th odd number? Well, maybe we need to figure out, is there a formula that gives us this? And the answer is, okay, I think I see it. What should it be? What kind of formula can I get that associates these so I can figure out what the 100th or the 101st, I should say, odd number?
Oh, is that a 3?
What do you think this is? This?
That was a 7.
All right, come on, look at the pattern. That is a 3. So wait a second. In your brain, you thought that I just threw a 7 in there.
That's why I was like, oh my God.
Sorry. All right, I'll fix that. But come on now, context clues. Here goes someone else. I thought the same thing. You guys are legends. That is poor penmanship on my fault, and I apologize. But come on, what's the context?
Well, you throw random examples in there sometimes, so I was like, oh my God. That's all that I figured out.
Yeah.
It might be a minor thing, but why didn't you write 1 in the on?
That's why I'm asking. It's not a minor thing. 1 should be there, right?
Oh my God.
What? Once you put 1 there.
And now you're not writing numbers.
No, well, I did that on purpose. The 7 was just poor penmanship. You're right. So there should be a 1 here. And once I put the 1 there, hopefully it's clear sort of what function I can use for this. 1, 3, 5, 7. So let me again, I don't want to give it away. Sometimes it's fun to do trial and error to see what the pattern is. So the function we're going to use here is f of n equals 2n minus 1. And you could check it. What's f of 1? 1. What's f of 2? Well, that's 4 minus 1, which is 3. This guy right here, you should show, it's very easy to do it. You should verify it is 1 to 1 and onto. So if I now know that, and then I can use this formula, what is the 100th term? Well, the 100th term is 199. How did I get that? Well, 2 times 100 is 200 minus 1 is 199. And then the 101 term, well, that's 202 minus 1, which is 201. And so what's the conclusion here? The conclusion here is that the odd numbers have the same cardinality as the natural numbers. And odd numbers are countable. That's sort of the conclusion. I guess this is a separate example. Things that you should do. So these are examples you should verify. Number one is that integers has the same cardinality as the natural numbers. And what you can use, one way you can do this is you can define f of n piecewise. You can say that it's n over 2 when n is even. And what is it? I think it's, yeah, it's n minus 1 over 2 with a minus sign when n is odd. So you can show, and I'll ask you to do this for homework. You can show that this function is a bijection, and hence the integers have the same cardinality as the natural numbers. By the way, again, what I would encourage you to do is write it down and visualize it, sort of like this. If you put, you know, the natural numbers here, what are the natural numbers? 1, 2, 3, 4, 5, etc. And then what are the integers? Well, one way you can list the integers is like this. You can say 0, 1, -1, 2, -2, etc. And you can verify that these functions, that function gives you the relationship. For example, just check. Think about the fifth term. What is 5? Is 5 even or odd? Well, 5 is odd. So you use the second formula. 5 minus 1 is 4. 4 over 2 is 2. So you get -2. You could check that this function, this piecewise function, works. The tricky part is showing that it's a bijection, but you can definitely do that. It's not terribly difficult. Couple cases to consider. Does anybody have a question about this? Here's the other example that is important, and that is, this one tends to be a little sort of trickier. The second one is that the rationals is also countable. Now, what you typically do to show this is you typically use some theorems, because it's not obvious that how to illustrate the function, like an f of n, blah. But it is clear to see that there is a correspondence. And the way you do that is quite simple. So let me say this. And if you're interested, obviously you'll Google it anyhow. So the quote unquote pattern is more obvious than the bijection f. So what you can do is you can think about it. Let's think about how we might list the rational numbers. Well, the first rational number, I shouldn't say the first, but one good place to start would be, say, okay, 0 is a rational number, right? But let's just ignore that for a second, because that's just one number. Let's say we wanted to list things out. Well, we can list, say you start with, let me change colors here. You start with, okay, I'll write the number 1, but instead of 1, I'll write it as 1 over 1. And then 2 over 1, and then 3 over 1, and then 4 over 1. And then this pattern continues indefinitely to the right. And then the next row we can do, okay, let's do everything with denominator 2, 1/2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, and that pattern continues. And then, of course, the next thing would be, let's go 1/3, 2/3, 3/3, 4/3, 5/3, and then we continue this, and we continue going horizontally and vertically. Now, a very clever thing is to think about how you might go through these lists. I mean, you're going to say, well, how do I count this? How do I go left to right? Do I go up to down? Well, the trick is, instead of doing that, is you do sort of a combination of both. You use this sort of diagonalization. You start here with 1, and then you go here. That gives you 1/2. And then you go up here. That gives you 2. And then you go here. That gives you 3. Then you come down here. You could skip this one because we already have this guy, right? 2 over 2 is 1. We've already accounted for that. And then you get to 1/3. And then, of course, you would go down to 1/4. And then you come back up. You'd have 2/3. And then you have 3/2. And then you'd come up here to 4. And then you'd go next door to 5. And then you come down. So there is a pattern here. So again, the ones that I'm circling them because that's the first time they show up in my list. And the ones that aren't circled, they're duplicates, so I can ignore them. 2 over 2 is already taken care of. It's the number 1. So if I go to the next page, I can start to see my list. Suppose I have my natural numbers again, 1, 2, 3, 4, 5, 6, etc., etc. And then underneath it, I'm going to have my new list. What's my new list? Well, it was 1, 1/2, 2. What was next? I think it was 3. Yeah, it's 3. And then it's 1/3. And then it is, what's after 1/3? After 1/3 would be 1/4. And then that pattern continues. And the difficult thing for you guys would be, what is the function that gets this done? Can I show that it's 1-to-1 and onto? Using some nice rule. So here's the question. What f f gives us this? That's what you sort of have to figure out. Now, if you're paying attention, if you're a good observer, the first thing you're going to say is, well, Grady, that just shows that the positive rational numbers are countable. And that's true. That's all that shows. But turns out there's a theorem that you can use later that says if you have 2 countable sets, their union is countable. So that means if I take the positive rational numbers and I union them with the negative rational numbers, that's going to be countable. And then if I add 0 to that, that's just one more term. So that's countable. So these are some deep ideas. I really encourage you, if you'd like to learn this stuff, you've got to spend some time on this. I don't pretend that it's easy, but I never do. Does anybody have a question? How much fun you're leaving?
Yeah, probably. I'm so confused.
You're confused. That's good. That means you're learning. See, this is what I'm always curious about. People always say, oh, this is so hard to learn. I'm lost. Well, if you already knew the stuff, why sit in the class? If it's easy, is it even worth learning? I don't think so. Well, I shouldn't say it's not, if it's easy. There's a lot of things that are easy to learn that are worth learning. But, you know, stuff like this it's definitely challenging. All right. Any questions or comments about this? All right, so there's a couple important theorems, and we're not going to prove them. We'll actually have you prove them for homework. It'll be fun for you. You'll hate it. So actually, this is the third example sheet because you need to know this too. This is extremely important. It's not easy to show. The third example is the following. The cardinality of 0 to 1 and I guess we can say that this thing is equal to this. The open interval and the closed interval are the same. And this guy is, or let's see, let me write it more clearly. And both are uncountable. So we'll ask you to do this for homework, and then we'll probably briefly touch on it on Wednesday. The proof is by contradiction. Well, not the proof, one proof. The standard proof. And it's called, or it's attributed to, the mathematician George Cantor. So this was a big problem, and it wasn't resolved until the late 1800s. I think this was like 1870 something. Now you're going to say, oh, whatever. But a consequence of this is that the real numbers are uncountable. All right, so these are three examples that if I were you, I would study and know how to do specifically. I will put them on the homework. But we've really done it for you. I mean, I gave you, for example 1, we gave it to you. Example 2, it's one I would encourage you to study and think about this diagonalization stuff. Example 3 on how the real numbers are uncountable. I mean, if you might going to say, why is that a consequence? Well, imagine if a subset of a set is uncountable, you would imagine the whole set is uncountable. So let's write some of these things down that you should sort of know. And we'll ask you to do them for homework. They're not difficult to prove. So here are some fundamental results you'll prove for homework. Number one is the following. So if A and B are countable, then the union is countable. If A is a subset of B is uncountable, well, let me be more specific. I should be very clear here so it's not. Let's be very specific. If A is uncountable, and A is a subset of B, then B is uncountable. If A is a subset of B, a proper subset, then the cardinality of A must be less than or equal to the cardinality of B. Does anybody have a question about these? So these are going to give, you're going to struggle with these. So hopefully you'll give them thought before we show you how to do them. And we'll give you, once you see the solutions, I hope you know, study them up. But these are some, you know, until you've seen proofs of these kinds of things, it's kind of hard to know where to start. But let's just sort of give you some hints. So for one, there's three cases to consider. The first one is A and B finite. The second case is one is countable and the other finite. Doesn't matter which one. And then the third option is both countable. Now, you don't necessarily have to break it down to 3. You can be more fancy, but this is probably the easiest way to see it. Now, the next problem, how would you prove that if A is uncountable, then any set that is where A is a subset of has to be, uncountable? Well, I mean, think about the definitions. The definition of uncountable, it means it's not countable, right? So what might be a strategy for this? What might be a strategy? So let me go back and emphasize that. What might be a strategy? It seems to us, at least by the definitions, that it's probably easier to show something is countable than it is uncountable. So maybe for part 2, you assume that B is countable and get a contradiction. Or can you go straight from the definition? So let me emphasize that. Should you try a contradiction? Or maybe that doesn't work. What about the contrapositive? So at some point you have to learn, or at least try to get these proofs written without, you have to sort of figure it out on your own. That's the only way you're going to do it. When you stare at it for 5 minutes and say, I don't know what's going on, I'm clueless, and then you just wait till class and then watch me do it, there's no learning happening. You got to try these things on your own, even if you don't get them right all the way. You got to try. So that's my other thought on that. And then last but not least, what was the third one? Oh, yeah. And then just for this one, just think of the definition. So why am I writing this down like that with question marks? Well, I'm not saying that this is absolutely how things are going to work. But I'm trying to give you different ideas. Sometimes if we want to prove something, like for example, if we want to prove something is countable, we show that it satisfies the definition. We say, okay, let's exhibit said bijection, said correspondence. But other times that might not be the best route to go. So we might have to get creative and try a contrapositive, or we might have to try a contradiction. You know, it's like the more tools you have in your toolbox, the more likely you are going to be, the more likely it is that you will solve these problems in a reasonable amount of time. So it is worth pointing that out. Again, I'm not going to pretend that this stuff is easy, but again, part of what we want to learn in this class is new math. This is new math. We also want you to be able to do proofs. And so that's what we're asking you to do. Writing proofs is a skill. It's not easy to get good at. But like all things, particularly in science and mathematics, the more you practice, the more you sort of engulf yourself in these things, the more you are sort of exposed to things, the more natural they become. It's just the way it is. Okay, that's a good place to stop. Does anybody have any questions, comments, concerns? So I'll post an assignment this afternoon. It'll be due Wednesday evening, so hopefully if you have questions, you can ask in class. All right, guys, thank you very much. Be safe, and I will talk to you Wednesday, if not sooner. Thank you.